Let's talk about quotients of rings by ideals. The easier case is that of a commutative ring. Let's begin with that. So suppose R is a commutative ring. Okay, remember when R is a ring, then R comma plus is an abelian group. Okay, and what you can do is you can take the quotient of R by an ideal. So let I be an ideal of R. So what's an ideal? It's a subset of R which uh, is a subgroup of R plus, the abelian group R plus, but also it has a property that if you take an element of I and multiply it by any element of the ring, the product is again an element of I. But now this point is that I is a subgroup of R. And R plus is an abelian group, so I is obviously a normal subgroup. Every subgroup of an abelian group is normal. So the quotient ring is defined as follows. The underlying abelian group, additive abelian group, is just the quotient group R mod I. This is the quotient group. What does this really mean? So its elements are cosets of I, left cosets or right cosets, they are the same. So an element of R mod I is x plus I. So the form x plus I, x plus the set of all elements that can be written as x plus an element of I. This is a coset of I and this is an element of R mod I. And now we need to define the sum of two cosets, x plus I plus y plus I. And here we follow our rule for taking quotients of groups. And so this is just going to be x plus y plus I. And it remains to define the product of two elements of R mod I. So product is again defined in the most obvious manner. X plus I into y plus I is equal to xy plus I. Now we need to check something here. We need to check that this is a well-defined product in the sense that if we modify x by something in I and we modify y by something in I, then this right hand side does not change. In other words, for well-definedness, need to check that for all x, y in R, for all a, b in I, we have x plus a plus I. So this is x modified by something in I times y plus b plus I is equal to x, y plus I. So the product does not change if we use different representatives of the same cosets. But let's look at this left hand side. So this by definition is x plus a into y plus b plus I. But that is xy plus xb plus ay plus ab plus I. Now this AB is in I because A is in I, right? And A multiplied by anything in R is still in I. This AY is also in I because A is in I, so AY is in I. Similarly, xb is in I because b is in I, so xb is in I. So these three terms are in I, and so they get absorbed in here. So this is just equal to xy plus I, which is what we wanted. So product is well defined, and then you need to check properties like associativity of the product, that there is a unit, and that it distributes over addition. But these are easily checked to be inherited from the corresponding properties for the ring R. I'll just mention that the unit of the ring R mod I is just the coset of the unit in R. The only issue is when I is actually equal to R. When I is equal to R, then R mod I is trivial, and then this ring cannot have a unit. Some basic results about properties of ideals and what they mean for the quotients of rings by those ideals. So firstly, let's recall the definition of a prime ideal. Definition. So again, R is a commutative ring. An ideal I of R is said to be a prime ideal if xy belongs to I implies that x belongs to I or y belongs to I. Why is this called a prime ideal? It has to do with prime numbers. So in the integers, let p be a prime. Then consider the ideal p. So if xy belongs to p, so this is just the multiples of p, positive and negative multiples of p. If xy belongs to p, then this is the same as saying that p divides x times y. And we know from basic number theory that this implies that p divides x or p divides y. And that's the same as saying that x belongs to p or y belongs to p. So the principal ideal generated by a prime number is a prime ideal. In polynomials, the principal ideal generated by an irreducible polynomial is a prime ideal. And now here's a result about quotients by prime ideals. Theorem: R mod I is an integral domain if and only if I is a prime ideal. Proof. So let's prove that suppose I is a prime ideal. Let's prove that way first. So suppose I is a prime ideal, and suppose so we want to show that R mod I is an integral domain. So let's take two elements of R mod I. So we want x plus I times y plus I. If this is equal to 0 in R mod I, that means it's equal to just I itself, then that means that in fact this is an if and only if. This happens if and only if. Well, by definition this is xy plus I, so if and only if xy belongs to I. And since I is a prime ideal, this implies that x belongs to I or y belongs to I, which implies that x plus I is 0 in R mod I, or y plus I is 0 in R mod I. So if I is a prime ideal, then R mod I is an integral domain. Conversely, if R mod I is an integral domain, we just reverse this argument. Suppose we have x, y belongs to I. This implies that x plus I times y plus I is 0 in R mod I, right? Because this is just x, y plus I. And since R mod I is an integral domain, this implies that x plus I equals 0 in R mod I, or y plus I is 0 in R mod I. But that's the same as saying that x belongs to I or y belongs to I. So I is a prime ideal. Okay. So there's another kind of ideal called a maximal ideal. Definition: an ideal I in R is called a maximal ideal if it is the largest possible, it's maximal among the class of all proper ideals of R. So if whenever J is an ideal which contains I, J is an ideal such that it contains I, then either J is R or J is I. So there are no ideals in between R and I. Okay, so yeah, we require this to be a proper ideal. If I is R itself, then we don't typically call it a maximal ideal. And theorem: I is a maximal ideal if and only if R mod I is a field. And here's the proof. So let's start with I being a maximal ideal. Suppose I is a maximal ideal. Now I want to show that any non-zero element of R plus I has a multiplicative inverse in R mod I. So let's take an element x plus I in R mod I. So x plus I is not equal to 0 in R mod I, means that x does not belong to I. Right? So it's an if and only if. So if x is not in I. So now consider the ideal J equals all elements of the form Rx plus A, where R belongs to R and A belongs to I. It's not difficult to see that J is again an ideal. So this is an ideal exactly of this form. J contains I. And it is contained in R. But notice that J also contains the element X, but X is not in I. So that means J properly contains I. So this implies that J is equal to R. In particular, the unit of R belongs to J. So that means that we can write Rx plus A equals 1 for some R in R and A in I. But that's the same as saying that R plus I into A plus I. So that is, sorry, not R plus I, X, R plus I into X plus I. This is equal to 1 plus I. Just by definition of the product, which means that R plus X, this means that X plus I has an inverse in R. Namely R plus I. So this means that R mod I is a field. Every non-zero element of R mod I has a multiplicative inverse. Conversely, suppose R mod I is a field. I want to show that every ideal of R that contains J is either I or R. So suppose J is an ideal that properly contains I and is contained in R. I want to show that J is actually equal to R. But then what you do is you look at the image of J in R mod I. So what I'm saying is you look at J plus I. So this is the set of all elements of the form J plus I where J belongs to J. This is a subset of R mod I, and in fact it turns out that J plus I is an ideal in R mod I. In fact, it's a non-zero ideal. Why? Because J properly contains I. So there is an element of J which is not in I, so there is at least one non-zero element in J plus I, a non-zero element of R mod I in J plus I. But in a field, the only non-zero ideal is the field itself. This is something you can check. This means that J plus I is equal to R mod I, which implies that J is equal to R. And here's a nice corollary of these two results. Every maximal ideal is a prime ideal. The reason for this is every field is an integral domain. Let's look at some examples of ideals which are prime but not maximal. Now if you look at the integers, the only ideal that is prime but not maximal, 0 is a prime ideal. This is just because the integers themselves form an integral domain. But it's not maximal because ideals of the form, well, it is contained in lots of ideals. All the other ideals of Z contain 0. And for prime number p, the ideal generated by p is a prime ideal and a maximal ideal. The only ideal larger than p is z itself. And this corresponds to the fact that z mod pz is a field. Okay, so it turns out that in the integers, most ideals are prime ideals. But let's look at a polynomial ring in two variables. So let's take, say, complex numbers and x, y. Then here's an example of an ideal. Let I be the ideal generated by x and y. So this is all polynomials of the form pxy times x plus qxy times y, where p and q are themselves polynomials in x and y. This is a maximal ideal. What you can show is that so this actually consists of polynomials with in two variables with a trivial constant term. Every term in this polynomial has to have has to be divisible either by x or by y. So there's no constant term, and that's the only condition. And what you can show is that R mod I is isomorphic to the complex numbers. How do you construct this isomorphism? Given a polynomial f, you map it to f of 0, 0. That's a complex number. And every polynomial that is in this ideal will get mapped to 0. And you can show that this is an isomorphism. So this is a maximal ideal, because the quotient is the field of complex numbers. Okay, but in Cxy, you just take the ideal generated by x. This is a prime ideal. Why is that? Well, remember, Cxy can be thought of as polynomials in y and then in x. So polynomials in the variable x whose coefficients are polynomials in y. And then if you take Cxy mod x, this is the same as taking Cy x mod x, but this is just isomorphic to polynomials in y. What this quotient means is that you're just setting the variable x to be 0. And so this is an integral domain. So the ideal x is a prime ideal, but this is not a field, so it's not a maximal ideal. In fact, this ideal x is contained in the ideal x comma y, which is contained in Cxy. When we take quotients in non-commutative rings, we need to be a little more careful. So let's try doing the quotient process which we did for commutative rings in the case of a non-commutative ring and see what goes wrong. So now suppose R is possibly non-commutative. Ring, and let's say I is a left ideal in R. that would mean that I is a subgroup of R plus, and for every x in I and R in R, Rx again belongs to I. Now I want to define a ring structure on the additive quotient group R mod I. So let's try to define a ring structure on R mod I. So we do this: x plus I into y plus I is equal to xy plus I. We need to check if this is well defined. Okay, so is this well defined? So as before, we just look at x plus a plus I times x plus b plus I and try to see if this is equal to xy plus I. But as we saw, this is y plus b plus I. So this is xy plus ay plus xb. Now we need to be very careful about left and right. Plus, and then we have by definition this is this plus I. Now I is a left ideal, so that means that this thing is of course in I. I is a left ideal, so that means that we have one more term here, a plus b, a times b. Okay. Now I is a left ideal, so that means that since b is in I, ab is in I. Since b is in I, xb is in I. But we do not know that ay is in I. So if ay is not in I, then this can go wrong. So what we need is, but this will be in I if I is a two-sided ideal. So we cannot work with only a left ideal, but we need to work with two-sided ideal. So let's take I to be a two-sided ideal in R. Then this will also be in I. And so we will get that this is equal to xy plus I as needed. So multiplication is going to be well defined on R mod I, provided I is a two-sided ideal. So the theorem is that if R is a ring, I is a two-sided ideal of R, then R mod I has a ring structure with multiplication given by x plus I into y plus I is equal to xy plus I. Again, you need to check that this multiplication product, this product structure satisfies all the axioms for a ring, and I'm not going to do all those steps. It's fairly straightforward. The main point is that this product is well defined only when I is a two-sided ideal, and that's what you need to take quotients of rings. Let us look at an example of quotient ring construction in the case of a non-commutative ring. So let Q be a quiver. So it's a quadruple VEST, where V is the vertex set of the quiver, E is the edge set, and S and T are functions from E to B, which tell you where each edge starts and terminates. And then we have E star is the set of all paths in Q, and the path algebra KQ is a ring. It's as a set. It's the vector space. It's a vector space with bases given by paths in Q, and multiplication is defined by concatenation of paths. This is the path algebra of Q. Now, what I had mentioned earlier and left for you to check was that if you define n to be the span of P in E star such that the length of P is positive, then n is a two-sided ideal. In fact, in Q there are two kinds of paths. There are the trivial paths. So we have the paths EI, I belongs to V. So this is the trivial path at I. It's a path of length 0, does nothing, just stays at the vertex I. And then there are paths of length, positive length. So KQ has a vector space over K. This is n that's spanned by paths of positive length, and then it's the direct sum over all I belongs to V K E I. So this is a complement of n. And this, therefore, we can define isomorphism from KQ mod n, just a linear map, to KEI using this decomposition. Get projection map KQ to direct sum I belongs to V KEI. What this map does is, if you have any linear combination of paths, you just take all the paths of length greater than 1 and send them to 0, and just keep the paths, the trivial paths. Okay, and this linear map phi has kernel exactly equal to n. So what we get is KQ mod n is isomorphic to I belongs to V KEI. And this in fact turns out to be a ring isomorphism. So what happens is that how is this a ring isomorphism? How is this right hand side a ring? So in this right hand side, the ring structure is just as if we had a quiver with no edges at all. So this is the path algebra of the quiver. I'll call it Q0, where Q0 is the quiver with the same vertex set, the empty edge set, and of course S and T are, well, don't need to specify them, they are functions from the empty set to V. So KQ mod n is actually isomorphic to KQ0, the path algebra of the quiver with no edges.